Morning, student. This is Mr. Teo again. Continuing from last lesson where we discussed about PID control. We will talk a bit on word plot today, which is the topic that is more intensive in terms of difficulty. So please pay attention.
In previous lecture, we talk about PID controller. This lecture we are going to continue chapter 5 by diving into Bode plot and stability. Note that for Bode plot and stability analysis, we will be operating in the frequency domain, i.e. the S domain.
So basically, last week we talked about the PID controller, where we start talking about what's the effect of P, which is looking at the present, the effect of I, which is looking at the past, and the effect of D, which is looking at the future. And then we start going into different configuration of PI, PD, and ID, and we look at the effects of each of the PID component itself. Then, of course, we did some tutorial question to explore a little bit on PID. So today, we will be moving into word plot, which is mathematically more intensive for this topic. So basically, students usually feel in the previous semester that this is a heavier topic. So please bear with me.
Recall in chapter 3 we mentioned about analog signal being made up of multiple fundamental frequencies, and when viewed in the frequency domain they are well spaced out.
Now, as we have already viewed this graph before, this is to recap with you the frequency, or rather any fuzzy signal in the time domain can be viewed as a summation of multiple frequency, and this summation of multiple frequency, looking at the time domain, is actually pretty fuzzy and mixed, so you really cannot separate which one from another. But if you come and look at the time domain, I mean the frequency domain, you realize that it is of a very distinct frequency component, well spaced out. So that's what this is all about, right? And each of these frequency domain are basically one single frequency component, right?
Each of the fundamental, single frequency, sinusoidal waves can be viewed as a vector with certain magnitude and phase, aka polar form. Please watch the animation on how a rotating vector is a sine wave when resolved onto the y-axis. For this case,
now I'd like to demonstrate one way to construct a sine wave. What we're going to do is we're going to construct something that looks like sine of omega t. So we have our function of time here, and we have our frequency. Now this little animation is going to show us a way to construct a sine wave. So what I have here, this green line, is a rotating vector. And let's just say that the radius of this circle is 1. So here's a vector just rotating slowly around and around. And in the dotted line here, in that yellow dot going up and down, that's the projection. That's the projection of the tip of the green arrow onto the y-axis. And as the vector goes around and around, you can see that the projection on the y-axis is bobbing up and down and up and down. And that's actually going up and down in a sine wave pattern. So now I'm going to switch to a new animation, and we'll see what that dot looks like as it goes up and down in time. So here's the plot. Here's what a sine wave looks like. As you notice, when the green line goes through 0 right there, let's wait till it comes around again, the value of the yellow line when it goes through 0 is 0. So this yellow line here is a plot of sine of omega t. Now, if I go to a projection, this projection was onto the y-axis, and I can do the same animation, but this time project onto the x-axis, and that'll produce for us a cosine wave. Let's see what that looks like. Now, in this case, if we switched over, you can see that the projection, that dotted green line, is onto the x-axis. And what this is doing is it's producing a cosine wave for us. So this is going to be cosine of omega t. Now, because we're tracking the progress on the x-axis, the cosine wave seems to emerge going down on the page. So the time axis is down here. When the green arrow is 0, right there, the value of the cosine was 1. And when it's minus 180 degrees, it's minus 1 on the cosine. So that's why this is a cosine wave. And it has the same frequency as the sine wave we generated. And now I want to show you these two together because it's just sort of a beautiful drawing. I'll leave our animation here for a second. We see our sine wave being generated in yellow, and in orange we see the cosine wave being generated. And they're both coming from this rotating green vector. So this is a really simple demonstration of a way to generate sines and cosines with this rotating vector idea. We're going to be able to generate this rotating vector using some ideas from complex arithmetic and Euler's formula. I find these to be a really beautiful pattern, and it emerges from such a simple idea as a rotating vector.
So essentially what this animation is trying to show you is that this particular vector itself with magnitude and angle, when it rotates around, if you were to reflect it into the x-axis, which is the real axis, or you were to in fact reflect it into the y-axis, you actually created both the sine and the cosine wave, which is your polar form, cos r theta plus by j sine theta, right? So you have actually a sine. So essentially what a sine wave or rather a sine wave in the time domain can mean a vector in itself. It's just one domain that it can be viewed as a vector, right? So
using the formula, polar form of a vector can easily be converted to rectangular form and vice versa. The rectangular form are essentially the complex number with real and imaginary j terms.
So this is essentially what we saw just now. What we saw in the video just now, this is the magnitude and the phase. So if I say x and y, x plus jy is actually r cos theta plus jr sine theta. So you can see that if you reflect it into the x-axis, it's a cosine wave, and if you reflect it into the y-axis, it's essentially a sine wave. So therefore, that's explain why there's a sine wave and cosine wave behavior in the animation just now.
Any signal when injected into a system will experience magnitude and phase changes according to the system's transfer function, i.e. the output over input of that system. The entire system's transfer function is, in turn, made up of asymptotes, Lego bricks. Each of this asymptote is like the fundamental single frequency sinusoidal waves in its rectangular form. For example, S plus 5 can be viewed as j omega plus 5 when we replace S by j omega.
Now, this is a normal transfer function of the gain transfer function g of S. So you have numerator over denominator, right? So of course, this numerator, I just use a real number. There is no S term in it. But in the denominator, I have 3 S terms. So this is S to the power, is a third order denominator. So this is just an example. So a transfer function looks like that. It has multiple solutions. So basically, there's one solution of S equals to 0. The other one is S equals to minus 5. And this other one is S equals to minus 8, right? So these are the 3 solutions, or we call it 3 asymptotes. Now, each of these, the whole transfer function is basically made up of all these small little blocks, and we call these small little blocks asymptotes, or if you cannot view it as asymptote, or it's too difficult this term for you, then it's like a Lego bricks that make up of the whole transfer function, right? So asymptote is like fundamental single frequency. So basically, what do you mean a fundamental single frequency means that it's a one sine wave. So if you just if you just view the S plus J5, we know that J is S is equals to J omega in is equal to j omega. So actually s plus j5, you can rewrite it as j omega plus 5. So actually there's a real term, there's an imaginary term, which is similar to the polar form that we see just now, r cos theta plus j sin theta. So therefore this is itself one vector by itself, and this is another vector, and this is another vector. So basically a transfer function is made up of multiple vector interacting with each other, right? Multiple vector interacting with each other, and of course forming a resultant vector.
Any signal when injected when the same system is placed under feedback for the purpose of controlling and converging the output to a desirable value. The stability of the system will be tested. As a signal goes through the system, its magnitude and phase gets shifted. When this happens, a negative feedback system may change to becomes positive feedback system. An oscillation starts to surface. Bode plot is a tool that uses the system's open-loop magnitude and phase plot to determine whether the system is stable.
So essentially, if each of these asymptote is one vector by itself, so it can be represented by r cos theta plus j sin theta, and also it can be represented by the magnitude form, meaning that the magnitude and the phase, right? So each of the magnitude and the phase will interact with each other, so forming the net magnitude resultant and the net phase resultant. So when you inject a signal into a feedback system, it will experience the phase and magnitude shift by the transfer function g, and of course plus its feedback. So as a net result, sometimes because of the feedback, instead of coming back as a negative signal to subtract the original signal, it comes back as a positive signal because of the phase shift due to the loop, right? The loop what it experienced. So therefore, sometimes because of all this, it might turn out to be oscillatory, meaning that it is not stable. So so if you are not careful, you hook it in a negative feedback fashion, hoping it to stabilize, but actually what happens is it becomes oscillation. So meaning that when it oscillates, your damping ratio zeta becomes 0. So this is a instability situation. Now, so basically what we use is we use Bode plot to check the stability when we design. So to ensure that a feedback system, especially the one that is intended for negative feedback, don't fall into the region of the positive feedback and oscillation. Okay?
Let's now dive into more technical about Bode plots. In Bode plot, we only analyze the system's open-loop transfer function, not the closed-loop transfer function. For magnitude and phase plot.
So basically, Bode plot, we of course look at the open-loop transfer function. Remember what is open-loop? Meaning that if you move your signal from input all the way through the forward gain, G of S, and then you loop back to your feedback gain, which is H of S. But before you close into the summing node, negative summing node, you actually open that. So it's actually G of S plus by multiplied by H of S. And this is the open loop transfer function. So basically in Bode plot, we always use, or in fact only use, open loop transfer function. But in a lot of time, when I started teaching the Bode plot, I told students, reminded a lot of time, please use open loop transfer function. But end up in the test or in the exam, they always use closed loop transfer function. Now, closed loop transfer function is more complicated, right? So to plot the Bode plot, it will be a lot more difficult than open loop transfer function. So basically, please take note, we only use the open loop transfer function. Now, open loop transfer function, what do we look at? Basically, we look at the overall magnitude. As I mentioned before, just now, each of these vector component will interact with each other, forming the net magnitude, and this is the net magnitude, right? And then also likewise, each of these vector component, which called the Lego bricks or asymptote, will have phase that interact with each other, and the net result of all the phase interaction will be your phase plot. So basically, we are using the net open loop gain plot and the net open loop phase plot to determine whether the system is stable when it's connected in a negative fashion, right?
Open loop will be the multiplication of all the blocks transfer function that lies along the blue dotted path. For this case is G1 S multiply by H1 S Let's go slightly deeper by defining what is a pole and what is a zero. After determining the open loop transfer function of G1, S, H1, S, we rewrite it in form of product of sum with numerator and denominator. Those roots, or solution, at the numerator will be called zeros. They are zeros so because when S equals to any of the roots, G1, S, H1, S, will become 0. Take for example as we put S equals minus Bn, then S plus Bn term will become 0. When that happens G1, S, H1, S, will become 0. Hence we call the roots of the numerator 0. As for poles, those roots, or solution, at the denominator will be called poles. They are poles because when S equals to any of the roots, G1, S, H1, S, will becomes infinity. Something that is infinity in height will looks like a pole. Take for example as we put S equals minus AD, then S plus AD term will become 0. When that happens G1, S, H1, S, will becomes infinity, because anything divided by 0 will be infinity.
Now, this concept sounds a little bit complicated. Maybe I will start to illustrate it using the blackboard, or rather the whiteboard. Okay, so if you look at it this way, we studied the block diagram manipulation many times, right? And we know that a block diagram manipulation can be formed by multiple blocks, right? So imagine if I have G1, G2, and G3, right? For example, I have 3G, G3 together, and which forms my forward gain. And then I have the feedback as H1, H2. I have H1 and H2. Example, this is just an example, right? And now, of course, I go into a negative feedback, right? So this is a negative feedback and this is the input. Now, what is then the open loop gain for this case? So open loop gain is pretty straightforward. Basically, it is the gain experience when we move along the forward going path, which is G1 times G2 times G3. Okay, if I call it G of S, right? G of S is equals to G1 times G2 times G3. So this is total, any block that is lying within from the input to the output, right? We call it the forward gain. So it is the experience of the gain moving forward, and then also the experience of the gain moving backward, right? Moving backward to where? To where the summing point is. So moving backward, you have H of S, which is equals to H1, H2, because H1 times H2. So that's what it experienced. So basically, your open loop gain don't close. Okay, so they basically is called open loop gain because this part here is open. So basically, your open loop gain will be given by basically G of S multiplied by H of S. And we call this the open loop transfer function. Now, this open loop transfer function, of course, each of these blocks can have a lot of sub-component, like, but for example, S plus A over maybe S plus B, S plus C, or each of the small, let's say G1 is like that. So when you multiply together, all of them together, your n open loop transfer function, which is G of S, H of S, will have multiple S plus, let's say, A numerator, S plus, let's say a lot of them, B numerator, dot, keep multiplying because we want to have product of sum, right? Then S plus Z n, right, numerator. And then, of course, you can also have, for the denominator, S plus AD, which is the denominator, S plus BD, all the way to S plus ZD, right? So this is for denominator. So this is a general form. It could be that complicated or it could be more simpler. But those, when we define, we try to define, of course, numerator and denominator. As I mentioned before, of course, in any transfer function, in a control block, the denominator is always the more important, but then also we need to know what is the numerator. So each of these will be your asymptote, or the Lego bricks forming the whole transfer function. Now, so each of these we call it a, what we call it, a 0. Now, why is it a 0? Now, if let's say s is equals to minus an, so your term s plus an will become minus an plus by an. So it becomes 0. When this term becomes 0, the whole transfer function will become 0. So any one of them that equals to the root, the whole transfer function will go to 0, and that's why it is termed as 0. Yeah. So it's termed as 0 because any one of them equals to the root, the whole transfer function collapses to 0, and therefore it is called a zeros, right? So if I say there's two zeros, then you know that there's two solutions on top, which s plus 1 or s plus 2 or s plus 1. So there is. So this is zeros. Now, how about the poles? Now, the poles, on the other hand, is what we look at in the denominator, right? The poles. These are the poles. Now, when poles happen, when the roots equals to, let's say, s plus bd, right? Then when the roots is equals to minus bd, this whole term becomes 0 because minus bd plus by bd will equals to 0, right? So when this term equals to 0, whatever numerator divide by 0 will result, the whole transfer function will result g of s, h of s to goes to what? Goes to infinity. Now this one result the open loop transfer function goes to 0, right? But this one go to infinity. Now infinity, why do we call it a poles? Infinity, in fact, is just a single point, right? If you look at it, it goes all the way up very high to infinity. So it looks like a pole, right? So therefore, this is called a poles, right? And that is called a 0. So that's the difference. Yeah? You call it a pole and a 0. Okay? So that's basically what it's trying to explain to you. So, of course, each of these are also single vector. Is like j omega plus an, j omega plus bn. So this is also a single vector, single sine wave. Oh, same thing. Oh, so this is what it means, right? When it goes to 0 or infinity.
Asymptotes each of these s plus an or s plus bd terms that make up of the whole g1 s h1 s transfer function. They are like the Lego bricks that build up G1, S, H1, S. In magnitude plot, we need to take the 20 log on G1, S, H1, S. By the nature of logarithmic function, any terms that multiply together, it will become addition. All the terms that divide it will become subtraction. In general, all the asymptotes at the numerator will add and all the asymptotes at the denominator will subtract. An example is given below to illustrate the effect of 20 log on the asymptotes.
So basically, this part we have already discussed in a whiteboard just now, that the final transfer function of the open loop gain, which is g of s, h of s, can becomes this form. Of course, it can also have a magnitude gain. This is just a simple magnitude. So, of course, if you write it in this way, then because for most of the magnitude plot, we will use the log scale. Later, I'll explain why we use the log scale. But basically, we will use a 20 log scale, 20 log the whole thing. Now, people ask me, why do you use 20 log? Why not 10 log? Okay, there is a reason behind why 20 log is used instead of 10 log. So maybe I should clear this and explain why it is 10 log and not 20, why is 20 log and not 10 log. Now, if you remember, you guys are triple E student, right? So triple E student, remember, power is equals to VI, right? Voltage times current. Now, what is actually voltage? Voltage is actually I sum R, right? IR. That is voltage, right? And then, of course, times by R. So basically, you are actually having I squared R, right? Or if you want to change the current, you move this way. So What is current? Current is actually V over R, right? Or you can say is V squared over R. So whichever it is, if you want to try to represent it in either of current form or of voltage form, right? You will result in a squared here. You result in a squared here. Now, why is the squared important? Now, let's say if I change this to a log scale, normally log scale we use 10 log, 10 log of P, right? Similarly, I will use 10 log for the, let's say I'm using the I current side, so I'll use 10 log of I squared R, right? Right. So what is 10 log of I squared R? Essentially, it is 10 log of I times by 10 log plus by 10 log of R. So it's actually equals to 10 log, 10 of course you put aside, of I squared plus by log of R, right? So basically you get 10 log I squared plus by 10 log R, right? So what happens when you have a square? It becomes 20 log I plus by 10 log R. Okay, just look at this term. Here, for the current, we have what? A 20 log here, right? Now, if you look at the voltage sense, similarly, we will perform a 10 log P, again, is equals to 10 log V squared over R, right? Whether you want to do it in this fashion or you want to say that, hey, I want to regroup this guy as V squared over square root of R squared. So it's the same thing, right? So you have 10 log V over square root of R squared. So it becomes what? 20 log V over square root of R. So right now, again, you have 20 coming out. So that's the reason why when you operate in the voltage domain or when you operate in the current domain, we use 20 log instead of 10 log, right? Okay, so that explains why 20 log is used, because in our book plot, we are always using voltages, or in any circuit analysis, you always use voltage domain. You don't strictly calculate power. So therefore, 20 log is being used. So basically, if you use 20 log on each of the term, if you use 20 log on each of these, the particular term, for example, I have, let's say I have a very simple G of S, H of S. H of S. Let's say I have a very simple one. I have S plus 1, S plus 2, then I have over S plus 3, S plus 4. Now, how do I do the magnitude plot? So magnitude plot, I would basically do so basically magnitude, I would say magnitude of G of S, H of S, right? Magnitude of G of S, H of S will be equals to 20 log of this guy, right? 20 log of S plus 1, S plus 2, S plus 3, S plus 4. Now, what is 20 log of S plus 2, 1, 2, 3, 4? So basically, if you remember your mathematics, if you 20 log, then you basically 20 log into each of them. Then 20 log for the numerator, it will be S plus 1, right? Of course, if the second term that is multiplied together, you use a plus, right? 20 log S plus 2. Now, likewise, in the denominator, you don't divide. Now you become minus 20 log S plus 3 and minus 20 log S plus 4. Now, which one is easier to work on? Do you like to work on this is a multiplication scale, or do you want to work on addition scale? For me, I would prefer add, right? Because add is a lot more simpler than multiply, right? So this is multiply, because I'm afraid you look at it as multiply also. This one, if you rotate it slightly, so this is add. So Definitely an add is a lot more easier than multiply. So therefore, if you convert into a log domain, one of the advantages is you just use simple addition and subtraction. Whereas if you don't convert it, then you have to do a multiplication. So for human brain, basically addition and subtraction is easier, right? So therefore, that is for the magnitude plot only. Remember just now we say that we only look at the overall magnitude plot or the phase plot of the open loop gain, right? So this is the magnitude plot portion. So you just use a 20 log the whole thing. You basically get plus minus each of the asymptote.
For plotting the asymptotes for magnitude plot, there are few standard forms. Firstly, for form 1, the gain term, this will be the 20 log of a constant number. If the constant number is positive, the 20 log will result in horizontal line above 0 dB. If the constant number is negative, the 20 log will result in horizontal line below the 0 dB. Secondly, for form 2, 0 at origin, it means the roots occurs at 0. As we know, roots at 0 is at negative infinity and can never be plotted in the semi-log paper. Hence, what is visible is only the positive 20 decibels per decade slope that crosses the 1 radian per second, 0 decibel point. Form 3, for the poles at origin. Only things that changes when compared to 0 at origin is the slope changes from positive 20 decibels per decade to negative 20 decibels per decade.
Now, let me finish all the forms for the magnitude before I explain what you mean by all these things.
For form 4, when plotting a 0 at root a radian per second, the plot will be horizontal 0 dB all the way till a radian per second and slope up at positive 20 decibels per decade thereafter till infinity. For form 5, poles at b radian per second, the plot will be horizontal 0 dB all the way till b radian per second and slope down at negative 20 dB per decade thereafter till infinity.
So I think after this one, you guys will be pretty confused on what I mean form 1 to form 5 and what does all this thing means. Basically, form 1, form 5 is a simple rule of thumb for you to look at the Lego bricks, that means the asymptote, and then from the asymptotes, how do you anticipate each of these asymptotes should look like that make up of the entire asymptote. So each of the asymptotes, for example, this particular asymptote S1 plus S over A will look something like that, right? And then 1 plus this, if this is in the denominator, 1 plus S over B, then you will look something like that. So basically, it's just trying to tell you that, hey, with this form, with this kind of form, you'll be able to draw the asymptote in this way or that way. So let's go to the whiteboard and get more elaborated on all these things. Okay, so this part we are clear. So I will clear this. Then we'll talk about basically there is 5 form, right? So if you allow me to revisit your this G of S, H of S, which is the magnitude form. Of course, if you take a 20 log of this guy, this is your magnitude. Can exist in, let's say, K, let's say S multiplied by S plus A, right? So this is 2 form. S, there's a S again here, multiplied by S plus B. Okay, so these are form 1, form 2, form 3, form 4, form 5. This form the 5 types of form. Of course, you can have S, A plus C, right? S plus C, but this is the same form as this, same type of form, so we don't discuss about this, right? So basically, we just interested in this 5 form, right? The 5 possible way the thing is being expressed, right? So now this is actually essentially is S is actually equals to S plus 0, but that's why we call it the origin. And likewise for this case is also S plus 0, right? So basically these two are this is a 0 at origin. We call it the 0 at origin. right? 0, why? Because it is in the numerator. If it becomes 0, the whole term becomes shut down to 0. At origin, why? Because the pole is at 0. 0 is origin, right? So this is what we call the pole at origin again. So this one is at origin, but these two are not at origin. But this is just a pure gain term, right? So if you do a pure gain term, of course, when you do a 20 log, each of these terms split up, right? So it's split up into 20 log k, right? Plus by 20 log s, plus by 20 log s plus a. So that's for the numerator part, right? Now let's say I change a color for the denominator s plus b, right? So I change the color so that it's less confused. So this is s and s plus b. So you can understand what I mean. So when it comes to the numerator, it's all add together. But when it comes to denominator, it will become minus 20 log s, right? And of course, minus 20 log s plus b. Now, of course, people might ask me, hey, Che, why you don't straight away strike off this and this? Of course, you can strike off, but this is for the purpose of illustration. That's why I don't want to strike off. I want to illustrate to you the 0 at origin as well as the 0 at poles. But of course, in the real application, if you see such kind of situation, you better cancel off because you can solve one less asymptote, right? Similarly, even if you didn't detect that it's the same at this point, you would have detected here, right? Because plus 20 log s minus 20 log s is the same thing, so you cancel out. So, but we want to investigate 1, 2, 3, 4, 5, this 5 form, which is the form that we talk about. So let's say this is form 1. This is, let's say, let me take another color. So this is form 1, right? This is form 2. This is form 3. For example, this is form 3. We talk about origin together, and this is form 4. And that is, the other one is form 5, right? Now let's look at form 1. So form 1, we talk about form 1 now. Form 1 is, how come it cannot be written? Let me just erase this because I reached the corner of the thing. So therefore it cannot be written. Now let's look at form 1. Form 1, we have equals to what? 20 log k. Now if k is, now there is two possibilities. K can be, one possibility is k can be greater than 0. That is positive, right? This is positive. Now when k greater than 0, if you look at the graph point of view, this is, in fact, if this is a 0 magnitude, then k greater than 0, you take a 20 log k, your 20 log k result will be above the 0 line. This is what I mean. When so this will be 20 log k, whatever value you have. Let's say if I put a value 20 log k, let's say k is 10. So 10 log with base 10 is 1, right? So the k 20 log k is 20, right? So this is k. If let's say k is 10, right? If k is 10, then imply that 20 log k log 10 will be 20. So therefore, you have the curve here above 0. This is 0, right? 0 scale, and this is 20, right? So it's above 0. Now, of course, on the other hand, k also can be less than 0. In fact, not greater than 0. It should be greater than 1. Sorry, I did this wrongly. It should be greater than 1, right? Not just greater than 0. It should be greater than 1, right? So more than 1 time. So now, if k is less than 1, meaning that it is a fraction, right? So 20 log of a fraction, let's say 20 log of 0.5. Imagine if k is 0.5. Now, what is 20 log of 0.5? You will end up in a minus value, right? So let me try 20 log of 0.5. You get 20 log of 0.5. You get minus 6 dB. So it's actually, if you press your calculator, this will give you a -6 dB. Right? So essentially, if your K is having a negative value, then you will plot below your 0 line. So this is -6, right? So that's what it means, the first asymptote. So a K can be positive, not positive, greater than 1 or less than 1. So the moment the K is less than 1, you would have a negative number after you press your calculator. When your K is greater than 1, when you press your calculator, 20 log of K, it will be a positive number above 0. That's what Form 1 is all about, right? Form 1 is straightforward, just 20 log K, a number that is greater than 1 or less than 1. Now, Form 2 and 3 are talking about the, okay, let's look at the Form 4 and 5 first. Form 4 and 5 are the normal, the usual S plus A or S plus B, right? So S plus A, S plus B is the usual kind of a pole, right, or 0. So let's say if we talk about Form 4 first, let's say Form 4, right? Form 4 is S plus A, right? Now S plus A, so you have 20 log S plus A, right? Now what is the root of this guy? This guy, the root is at S equals to minus A, right? So if you take a magnitude, it is actually 20 log magnitude of S plus A, right? Magnitude means that no more sign. So that means the solution must be S equals to A. Agree? Or S equals to A. Therefore, then your 20 log stands, right? So basically what it says that if you have this kind of form, right? Of course, you can further normalize it by taking out the term. Of course, in your expression, if there is this kind of form, you can still normalize it. Basically, this term here, for example, if I want to normalize this term to S divided by A plus by 1, and I bring out the A. So it's A times S over A is S, right? A times A is A times 1 is A. So basically, this term can be rewritten as that. So that's why in your just now that page, we are talking about this form. Basically, is 20 log S over A plus 1, and not this form, but they are actually essentially the same thing, right? Whether it's 20 log S plus A or 20 log S over A plus 1, it's actually the same thing. Why? Because to find the root, is S plus A equals to 0, right? So A is S is equals to minus A. So if you take S over A equals to basically 0, plus 1 equals to 0, then your thing is also S is equals to minus A. So it's the same thing, right? You can see that both of them give you the same result. So that's why it means that the roots is the same. So in the frequency domain, when you see such kind of signal, and especially it lies in the numerator, which we call the 0. So in the 0 sense, you will plot above the 0 line, right? This is a 0 line. You will plot above the 0 line, and you will slope upward, right? At 20 dB per decade. Now this 20 dB is related to this 20. You can see that this 20 is related to actually this 20. The 20 is caused by this. So it's 20 dB per decade at this kind of slope. Right. Now, where is the turning point? The turning point is basically at your roots. Your roots is A, so it must turn at A. So that's as simple as that. So if I have a plot, right, and a pole like that, then my line will be coming from negative infinity. That means all the way to very far, and at the roots of A, it will turn up. It will turn up. So this is for Form 4. So this is for Form 4. Form 4, right? So it's quite straightforward, right? Now, Form 5 is a similar, but except right now we are talking about the denominator, right? So basically, we are talking about minus this case, right? So with a minus, of course, if you have a slope with a minus, let me go back to black color. With a minus, of course, B can be different position. Let's say B is here instead of here, and B can also be below. So if B is here, then of course you will slope down because of the minus sign. This is minus 20 dB per decade. So this is now minus 20 dB per decade for poles, right? Because it's of the minus sign, right? Can you see? Minus and minus. So this is form 5, right? And of course, if you were to see such kind of 20 log, or rather minus 20 log S plus B, right? Or rather you have minus 20 log S over B plus 1 is the same thing. Or if you have 20 log 1 over S plus B, it's the same thing. All three are the same thing. All referring to the same thing, right? All three are belonging to the same. It's just how you manipulate it, how you write it, right? So basically, if any of this form appear, then your pole will look something like that. Again, it's from negative infinity, it goes straight all the way. So it's from negative infinity again, and it hit B, which is the roots, which is the roots here. Then it will turn down. It will turn down at minus 20 dB per decade. Of course, this is also to negative infinity, and likewise, just now that one is also to positive infinity. So these are, we are talking about to infinity and beyond. So therefore, that is form 5, right? That is form 5. In fact, this is form 5, correct? This is form 4 and form 5. So this is form 5. So we have just discussed form 3, 1, 2, 1, 4, 5. Now what about form 2 and 3? Now form 2 and 3 basically are poles at origin. That means your poles is no longer having a value. Like for example, this case is S equals to minus B, right, for the pole below, and this one is S equals to minus A. You have a certain value. But now if you are talking about S, so form, let's say form 2, let me change the color back to black. So let's say now we are talking about form 2, right? Now form 2 basically is 20 log S. Now 20 log S is also equivalent to 20 log S plus 0, right? So if S plus 0, that means your solution must be S equals to 0. Whereas this case is S equals to A or B, right? But this is S equals to 0. Now S equals 0, if you put this to 0, can, but very far away. You understand what I mean? So meaning that if I have a 0 on top, intuitively, if you think the same way as form 4 and form 5, then you should have a turning up, right? If it is a 0, turning up at 0 frequency, right? 0 frequency, right? Right? This is not wrong. This is correct. This is correct. But then the problem is, in the log scale, 0 is like negative infinity. It's very far away. So essentially, you cannot see this 0. 0 is like never able to put it into the scale. I'll explain why 0 is never able to. So it's like negative infinity kind of case. Right? So you won't see this point. It's very far to the extreme left. So what you can see is only when your frequency becomes what? When your this thing become 1, right? 20 log 1. Log 1 is actually what? Log 1 is actually 0. So when your S become 20 log 1, right? When your S equals to 1, and that is the point where you can see, so it will come all the way, let's say, instead of looking at the 0, which is very far away, you cannot see. So for the 0, you will have a sloping up, meaning that it continues from very far away, come up to here, and at this 1, it will cross the 0. And when S equals to 1, the magnitude will be 0. This is 1 radian, magnitude will be 0. So this is the form 2 that we are talking about. This is form 2. So form 2 will look something like that, right? Look something like that. Form 2. Right? Now, similarly, for form 3 is just basically below, right? So form 3 is basically 20 log 1 over S, right? Or minus 20 log S. So again, this is minus 20. Yeah? So basically, for form 3, if I change the color again, it will be sloping down at minus 20 dB per decade. Just now that one is minus plus 20 dB per decade. Yeah? So it's always plus 20 dB per decade or minus 20 dB per decade. So this one is minus 20 dB per decade. 1 decade is 10 times. Huh? So this is plus 20 dB per decade. So plus 20 dB per decade and minus 20 dB per decade. Right? So basically for form 3 and form 4 is just this kind. One is of a positive gradient. Sorry, for form 2 and form 3, one is of a positive gradient and one is of a negative gradient. But the point that go through is the same. That means 1, 0, right? So this is form 3 and form 4 for you. So it's pretty straightforward, right? So you have form 4, 4 forms for the magnitude plots to occur, right? Right. So let's proceed again to look at the other page. So that is for the magnitude plot alone, right? So
using the 5 forms for all the magnitude asymptotes plotting. Each asymptotes can be drawn onto the magnitude plot. After that, summation is done on all the asymptotes to get the green dotted line. The green dotted line is still not final as we still need to shift the green dotted line by the gain term to the green solid line. The green solid line will be the final gain plot.
So this is if we put down all the asymptotes. Say for example we have one asymptote for S at origin for the pole and one asymptote for S at origin for the 0. So basically these two can cancel out, but I'm showing to you because we need to put it out, right? So then you have one for all the red one, you are having the 0. So you got 3 poles going 3 0 going up and 3 poles going down at minus 20 dB per decade to infinity, all of them. So if you have all these laid out in this fashion, for example, the absolute value, I don't know, this could be 1, this could be 2, this could be 10, this could be 15. That is the absolute value. Now we don't care about absolute. Let's say the relative position is this way, right? Now, if the relative position is this way, of course, we haven't considered the K term, the DC gain term. So we just don't care about the K term first, right? K term later we'll deal with it. There's another page on the K term. So let's not talk about the K term. Let's talk about the S at 0 and S at non-zero for the numerator, which is the 0, and denominator, which is at the pole, right? One is at origin and some are not at origin. So you have some at origin and some not at origin, all laid up in this relative position, right? So right now, your goal, remember, for 20 log magnitude scale, the 20 log scale is basically to tell you to add up, right? Add or subtract. So basically you add or subtract all this, right? So you have one pole going down, one pole going up. These two add together, you are flat, basically from all the way from negative infinity until this point, right? Now at this point, you have 1 0 going up, right? 1 0 going up, but no pole going down. So you have to follow this guy, the dotted green line, right? Now at the second point, AD, the going up is nullified by the going down, so it becomes flat, right? Now at BN, additional going up, right? Because the original going up still going up because it's to infinity, and then the second going up adds, so it's 2 up, 1 down. So 2 up, 1 down is net result is 1 up, so it's continue go up. Now at this point, BD, another pole come up, so it's 2 down, 2 up, right? 2 down, 2 up is flat. So basically it's flat all the way because there's no more additional pole or 0, is flat all the way, right? Flat all the way. And then when it hit here, 1 pole come, so its net is 1 down, so it's 1 down, it's slope down, right? When it comes to Zn, net is back to 0 because the pole and the 0 nullified, so it's back to 0. So that's how you continually look at each of the junction where you encounter and pole at 0, and you slope up and down based on that. So the net result will be the green dotted line, right? Now, where does the gain come into play? The gain, let's say, come into play because of the whole thing shift. So for example, after 20 log K, your gain value is, let's say, this solid black line, right? So you basically shift your dotted green line up to this level. And that's basically how you should shift your final gain to that particular portion. right?
To determine the gain term, all the asymptotes need to be normalized into form with bracket 1 plus s over roots. The common constant value taken out during the normalization is then multiplied with the original gain to determine the actual gain used. Another way to do it is to set all the s term to 0. Then the DC gain can straight away be determined. Both methods will arrive at the same gain value.
Now, of course, just now when I explained to you or share with you, I didn't tell you that K1 is the actual K value or K2 is the actual K value. In fact, if you were to intuitively think, you would think that it is K1 over K2 is the actual gain value. But then because of the fact that we need to normalize out, right? We need to take out the AN term. Remember, if you want to normalize this to 1, you divide by AN, divide AN, you bring out 1 AN. Right? Likewise for the BN and ZN. Right? So likewise for the denominator will be AD, BD, and ZD. Right? So you have a chunk of a common factor that is bring out in order to normalize the other side to 1. So this chunk of common value, common factor that is brought out, got to multiply with your K1 over K2. And this form your total DC gain. Or this form your total DC gain. And the actual, this gain is actually 20 log of your total DC gain and not just 20 log of K1 over K2. So it's 20 log of a total DC gain. Now, if you find this method very difficult to compute, then you can just set S to 0. So if you set S to 0, of course, ignoring that these two is there because these two rightfully should cancel out. So you set all the S to 0. So it's 0, 0, 0, 0, 0, 0. So you will have K1, K2, then AN, BN. So it basically just multiply when you set them to 0. So it's actually the same result, right? Because it's a DC gain. Or DC is occurring at the point when S equals to 0. Okay? When the frequency equals to 0, J omega. Omega is 2 pi F, right? If F is equal to 0, then it's 0. So therefore, DC they get no frequency value, right? So that's how you determine your gain value. So this is a little bit tricky also, but it takes time. You practice a few rounds, you should roughly catch the ball, right?
Similar to the magnitude plot, the phase plot has another 5 forms for plotting the asymptotes. From 1, for the gain term, the phase will be 0 throughout the frequency spectrum. Form 2, for 0 at origin. Again, what happens at 0 radian per second will not be visible to us as it is very far away. Like negative infinity in the Bode plot. Hence what we see is the final phase, a horizontal positive 90-degree line throughout the frequency spectrum. For form 3, poles at origin, the visible phase will be negative 90-degree line throughout the frequency spectrum instead.
Of course, again, we will be just now we talk about gain plot, and now we are talking about phase plot. Remember, the plot has the on top is a magnitude plot and the bottom is your phase plot. So we just completed explaining how to come out and draw the magnitude plot, but below it we still have one phase plot which we haven't plotted. And then this phase plot also have 5 forms, and that 5 form is actually related to the same kind of form that we are talking in the magnitude. But of course, in the phase plot, the way you draw it is slightly different from the magnitude plot. So this one, it shows you 3 forms. Then I'm going to continue with the other 2 more forms. Then later
for form 4, when plotting is 0 at root A radian per second, the plot will be horizontal 0 degree all the way till A over 10 radians per second and slope up it. Positive 45 degree per decade until 10 radian per second, whereas reaches positive 90 degree. Thereafter it maintain a positive 90 degree till infinity. For form 5, poles at B radian per second, the plot will be horizontal 0 degree all the way till B over 10 radians per second and slope down it. Negative 45 degree per decade until 10 B radian per second, whereas reaches negative 90 degree. Thereafter it maintain at negative 90 degree till infinity.
So basically, let's go back to the whiteboard. And now, instead of talking about the gain plot, now we will talk about the phase, right? So let's erase first. If you want to refer back, you can always play back the video. So magnitude and phase is slightly different. Magnitude, you will use 20 dB, right? 20 dB. So magnitude, we keep it there, 20 dB. There's the form, 5 form, right? But the phase, slightly different, right? So just now we talked about magnitude. Of course, now we are going to talk about the phase, right? So again, it's the same 5 form. It's the same 5 form, but then now we look at it in the magnitude sense. So the same 5 form will be again the gain, the pose at origin for the numerator and denominator, and of course the pose at non-origin for numerator and denominator, right? So it's going to be the same form because these are only the 5 type of form that is available, right? If you want more, also don't have, right? So these are only the 5 type. But for phase, basically we just look at phase, right? Phase of, instead of gain, we just look at the phase, right? Phase of basically G of S, H of S, right? Of course, if you take the phase, basically it will be the phase of K itself, whether there is any phase, and a phase of S, and a phase of S plus A, right? Over the phase of S again, and the phase of S plus B, right? So basically it's just the phase. Instead of 20 log, we are using the phase, right? Now phase of K usually is 0, right? Is a constant number. So phase of K usually will be 0 degree, right? So phase of K directly 0 degree. Now phase of S, the second form and the third form, first of S or at numerator or denominator, usually will be, S will be plus 90 degrees, right? Or this is form, let me write first. Let's say this is form 1, usually is 0, right? Form 2 is positive 90, right? Of course, the third one, if I put the same order, then it is plus by, oh, this one is no longer, is no more the angle in that sense. So this is actually tangent inverse. This is tangent inverse of omega over A, J omega, it should be omega over A, right? So this is plus tangent over omega over A. So this is, if you look at the vector point of view, let's say this is A, right? And omega is here, this is omega, and this is your A, right? So opposite, it should be A over omega over A. Let me double confirm. Omega over A, correct. So this is, for example, this is omega and this is A, right? Tangent is opposite over hypotenuse, so it's omega over A. So this is your theta, right? So tangent omega over A. Oh, so it's tangent inverse of that, because if you tangent theta, for this case it is omega over A. Omega is this length and A is the adjacent, opposite over adjacent, right? So this basically is tangent inverse omega over A. Then of course for the denominator, I should use the same analogy. So it's angle using the red color, and I use a B, S here, and angle of S plus B, right? So in the same sense, this one again, it will be, so this is the phase is plus together for numerator, but for denominator again is minus, right? minus, this is 0 degree again, right? 0 degree for this guy at S at origin, and then of course minus by tangent inverse of omega over A. Sorry, omega over B this time around, not A. Right? So this is basically you have 5 form already, right? So this will be your form 5, and this will be your form 3, and this will be form 4. So you look at it, form 1, very straightforward, right? Sorry, this is minus 90, not very careless. Should be minus 90 here, because S is minus 90, right? Only one of them is 0. So form 1, very straightforward. DC gain is 0. There's no gain at all, no phase at all, so it's 0. Now for the pole and 0 at origin is always 90 degrees, or plus 90 degree if it is at the numerator, minus 90 degree is if it is at the denominator. So this is also very straightforward, right? So very straightforward. But if you're talking about the other one, tangent inverse, this one is a more complicated one, right? So basically what it means is, if you form one, if you want to find out the phase of K, is actually essentially equals to K at 0 degree. So what you need to plot on the graph is basically 0, right? So if this is your axis, just plot 0. So this is basically your phase, right, at 0 degree. So form 2 and 3, 2 and 3, right, and 3 basically are for S and minus S and 1 over S, right? S is basically 1 with 90 degrees, right? Minus 1 over S is actually 1 over 90, which is 1 minus by 90 degree. So one of them is plus 90, one of them is minus 90. So essentially, when you have this 0 line, the one that is plus 90 will be the one at the 0. So this is your plus 90 degrees. And of course, the one at your minus 90 degrees will be the other one here, which is minus 90. Right? And of course, that one just now is a plus 90. So basically, that's the form 2 and form 3. Very straightforward. Now, form 4 and form 5 is slightly more complicated. Now, it is unlike the magnitude plot, whereby you just have a point, you slope up. Now, you look at the A itself and the B itself, right? Say we talk about form 4 right now. Undo. Let's say we talk about form 4 right now, and let's say we talk about form 4. Now, form 4 will be, again, same thing, having the root at A. Right? Form 4 will be having a root at A. But you got to meddle with the frequency at 10 times of A. So 10A. And you got to meddle with frequency at A divided by 10. That means 1 decade up and 1 decade down. So for example, if A is 10, right? A is 10. 10 times up will be 100 hertz, right? 10 times down will be 1 hertz. Oh, so that's what I mean. Oh, so for such kind of thing, for any pole and 0, the net shift of the phase will be always from its origin to 90 degrees. Any 0, right? Any 0 on the numerator, you always shift up to 90 degrees, right? So for form 4, which is the S plus A at the numerator, you would have shift up, right? Shift up, meaning what? It will shift up by 90 degrees all the way up to here, and it stop when it hit 10A, and you go down this way, go straight this way. So basically, it start at 0. You will start turning at the point where it hit A over 10. So this point where at A, this is at A, it is at 45 degree. So that's how it goes. It will start at A over 10, it will end at 10A. And the slope is actually 90 degree per 2 decade. Now it's not 1 decade, it's 2 decade. 2 decade. Right. So similarly for Form 5, is also the slightly different. Form 5 right now is because it is a pole, and then of course again the frequency will be from B over 10 to B to 10B, right? Of course, B and A can be some value. So for example, this guy is 20B, I don't know. 10B will be 200, right? And then B over 10 will be 2. So that's what I mean. So I don't know what is the absolute value of each of these terms. But of course, in order to draw it below, I got to change this guy here. And of course, again, the total shift of any pole or zero will be 90 degrees, right? So for this case, because it is at bottom, so you'll be shift to minus 90 degree, right? So basically, you have also it start from flat at the origin and it start turning at B over 10 and it will stop at 10B. So basically, it start turning at this point, go down all the way, right? Go down all the way, and then you stop here and you proceed straight. So just now that one, this one right now here is minus 90 degree per 2 decade. Right? Just now that one is plus 90 degrees per decade, right? Remember this one is plus 90 degrees per 2 decade. This is minus 90 degrees per 2 decade. And similarly, for the case of the pole, you're at the root, it will be at minus 45 degree. So that's the difference. It has to take care of 1 decade up and 1 decade down. Or it don't just turn at the root like the magnitude plot. The phase plot look at 10 times up, 10 times down, and then they say that hey, the pole would, the phase will shift in this kind of fashion. Now another way of interpreting is, in fact, the origin also behave this way. But then the origin is, for example, this is. Let me try to get the. Let me try to get the origin up first. So let's say right now here we have instead of 10, if this is the origin, so basically your this guy will be 0, right? If it is origin. Now 0 times 10 is what? Is 0. 0 divided by 10 is what? Also 0. So basically, the three things all collapse together, right? All collapse together at one point, right? Because everything is 0, and it just shoot up and go all the way up at 0. Because everything collapsed together. You understand what I mean? So that's why at the end, when you see it, you got plus 90. Right? Of course, for 0 at here, it's the same thing. 0 at the denominator, it will be the same thing. It will be everything collapse at 0.0, and it go down all the way and minus 90 degrees. Here, so you see a minus 90. So that's the reason why you see positive and minus 90. But in the very far end, you have slope up and slope down. But the slope is very steep because this is 0, this is 0, and this is 0. So everything is 0. Understand what I mean? So that is the 5 form again for the phase plot. Let me continue the lecture. Okay, so this is the 5 form for phase plot. And again, same thing.
Using the 5 forms for all the phase asymptotes plotting. Each asymptotes can be drawn onto the phase plot. After that, summation is done on all the phase asymptotes to get the green solid line.
Now, same thing.
Final phase plot.
So same thing, like the game plot, if you put each of these asymptote onto the graph, the scale, what you finally need to do is to add all of them up. Now, the good thing about phase is there's no DC shift, right? So what you see is what you get. So if let's say there is here I put down 6, 3 on the numerator, 3 on the denominator. So 3 0 and 3 pole plot, right? So you have 3 on top and 3 below. And what happens is, of course, again, you have to sum them up. So at the very beginning, everything was 0, so you just don't need to add. When you encounter the first one, you just slope up. And the second one, it will cancel the first one, then you have a flat slope. When this one stops, you just follow this guy down, right? The top face is gone already, so you just follow this one down. And does it go down all the way? No, because at this point, the bottom face stop, but the top face go up, so you have to follow the top one. Until about this point, you flatten again because it's one up, one down, right? And then once this guy stop, you proceed to down following this guy, right? So when this guy also stops, so all stop already, so it's flat, right? So when this guy go down, right, because it's only one line, and it stop when this guy go up, right? So it's neutralized. Now when this guy stop the face, it go up following this slope face, and then finally it goes out this way. So of course, intuitively you can calculate the number of, because each of the pole finally will introduce a plus 90 degrees, and each of the 0 will finally introduce a minus 90 degrees. So the final result is, let's say you got 2 0 3 poles. So you introduce 2 times 90, right? But you introduce 3 times minus 90. So the net result will be minus 90, because 3 of them below, 2 of them on top. So the minus one is stronger. So the net, if you add them all using 90 degrees, 90 for two of the 0 will be 90, 90, 180. Then minus 90 for 3 of the pole will be 90, 90, 90, which is minus 270. So 180 minus 270, you got minus 90. You understand what I mean? So you can use that as a check. So for this case, I have 3 poles, right? 3 0. 3 0 is 90 plus 90 plus 90 is plus 270, right? So I have 3 0 as well. 3 poles as well, which is minus 90, minus 90, minus 90. So I have minus 270 also. So I have plus 270 and minus 270. That's why my ending, it is 0, because 270 minus by 270 is 0. So that my end result is at 0. So that tells you what your end result should be. Ken?
The reason why we use logarithmic scale for the frequency x-axis is because frequency range can be quite huge and it's almost impossible to put it on a linear scale paper. When log scale is used on the x-axis, the range of frequency we can plot on a semi-log paper become very much wider.
Now, you realize that for a semi-log paper, it start off, like say, for example, I have this scale of 1 to 10. Right? It start off 1, 2, very wide. Then 3 becomes smaller. 4 become even closer. 5 closer, 6 closer, and up to 10. It's very close. But the next scale, it is 20. It's no longer 11. It goes from 10 to become 20, 30, 40, 50, 60, 70, until 100. Then 100, you jump to 200, 300, 400. That's how the log scales go by. Now, why is it that we want to use a log scale? Now, take for example, you encounter a lot of frequency calculation in your engineering so far, right? Year 1, year 2, now year 3. Now, a lot of frequency, they tell you in terms of kilohertz. Kilohertz is 1,000, right? So where is 1,000 here? You got to plot 1,000 times, very far away. How about 1 megahertz? You have 1,000, 1 with 6 zeros, so your scale will be humongous. Then what about 1 gig, 1 tera? Wow, this is like you plot from here to Orchard Road also cannot reach, right? So the scale will be huge. Therefore, in frequency plot, we would like to use logarithmic, because logarithmic squeeze the whole frequency, whole x-axis range to a manageable range, because it always jump tenfold, right? Every 0 to 10, then 10 to 100, 100 to 1,000, 1,000 to 10,000, or something like that. So it jumped tenfold. So as a result, you see a frequency domain plot that is being squashed to a visible range that we can put it in a scale. So that is what we mean by logarithmic scale. We need it because so that we can see the entire range and not to go all the way until Orchard Road to find out what is the actual value, where is the pole. So you take a very long time to search for a pole. But then in a logarithmic scale, it makes sense, right?
One thing to note is When using the semi-log paper, it must be an upright landscape orientation. For upright, you need to ensure that the wording printed on the paper is not inverted.
So usually for MYP semi-log paper, they will have a wording on top or below. So whether you want to ensure that the graph paper is in an upright movement, whether it's upside down or downside up, because it's in a landscape mode, it cannot be portrait mode. Some of the students go and use portrait mode and draw for me. I wonder how they learn, but it has to be in a landscape mode. So if it is a landscape mode, there's two possible directions. One is the upright and one is the inverted upright, right? So if you are in the upright, your scale will go from, for example, here is big to small. That means 1 and 2 is big, then 3 is getting smaller and getting smaller. So it's from getting from big division to small division. This is the upright. This is the correct position. But the other one, if you flip it around, then you will be from small to big. Then that is not correct. So the easiest way to identify is by looking at the words at the corner. If the words is upright, then you are in a correct, not inverted sense. So that's the rule of thumb for you to take note.
Please note that the magnitude and the phase plot have to be both aligned on the same X scale. Note also that the magnitude plot need to be on the top half of the paper, whereas the phase plot, lower half of the paper.
Now, for magnitude and phase plot, it has to be plot concurrently together using the same scale. Why? Because the book plot is not plot just to be nice, to show you that that's how a magnitude look like and that's how the phase look like. It's not that. Basically, we plot the magnitude and phase plot together, make sure it's in line. So later, we use the analysis on it, analysis on the magnitude and analysis of the phase to determine the phase margin, gain margin. And as a result, we infer whether this is a stable system or not a stable system. So that's the key of the thing. But then remember, when you do your magnitude plot, summing all the 20 log thing, you got to draw it all above the top half. Whereas you are doing the phase whereby you're doing all the 90 degrees thing, 45 degrees, 90 degrees, that one you have to do it at the bottom half. So what I normally do is when I take a semi-log paper, I determine the orientation, I know the landscape, I just fold it by half, right? Roughly fold it by half. So I know that, hey, I shouldn't exceed the half line for the magnitude plot to the bottom, or likewise for the phase, I shouldn't exit the half line to go to the top. So therefore, it ensures that each of the plot has sufficient space to be drawn on the scale, right?
Please watch the bode plot example to have an animated idea how bode plot can be plotted.
All right, welcome folks. We're gonna do body plot example for our students here. So in this example, we are asking you to draw body plot of the following transfer function, where I give you the transfer function here, h of s to equal to 40 times 1 plus s over 10 over s times 1 plus s over 50 times 1 plus s over 200. So it is very clear that in this transfer function, we have 1, 0 located at 10. We have one pole at the origin, one pole located at 50, and another pole located at 200. And the gain of the transfer function is 40. So the first thing we have to do is we need to plot the magnitude. And when we plot the magnitude of body plot, what we want to do is we want to get the magnitude, the 40, we want to convert this gain to dB. So we say that the gain in dB is basically the 20 log of the 40. And when you evaluate this, you get roughly 32 dB. Then what we want to do is we would like to use the semi-log graph. This is a semi-log graph to plot the magnitude. And the first thing we need to look at is we need to define the range of the frequency. So we have to think of the range of the frequency. And we need to think 2 steps ahead of us. The first one is we needed to know that when we do body plot, we plot the magnitude and the phase. Then when I wanted to specify the range for the frequencies in the log scale, I need to make sure that I will be covering the range required for the phase. because the first corner frequency or the lowest corner frequency is located at 10, then for the phase, I need to start a decade earlier. So I will make sure that this will read, the first segment here will read 1, then 10, then 100, then 1000, and so on. So this is because I know that the phase must start a decade earlier before the smallest frequency. So when I look at the range of the frequency, I see that it starts at 1, then 10, then 100, and then 1000, 10,000, and 100,000. Now, when we wanted to plot the gain in dB or the magnitude in dB, I need to specify the range for the gain in dB. So I need to be a little bit careful. I know that I will start at 32 dB. Then I will have a 0, and the 0 will go 20 dB per decade to the top. And I will do that for roughly about half a decade, because at 50 I will flatten out, I will get another 0. So I would say that I would choose the 0 somewhere in the middle, the 0 dB somewhere in the middle. And then if I will do that, then I will also decide that each interval over here will read 20 dB. So if this is 0, then this is minus 20, this is minus 40, and so forth. If this is 0, then this will be 20, 40, 60, and so forth. So when I do the range in dB, that's what I do, is minus 40, minus 20, 0, 20, 60, 40, and 60 dB. This is very important. That's something you have to think of by looking into the transfer function. You want to make sure that when you do the plot, you have the right range for the frequency and the right range for the dB to cover all the details required in the graph. Then what we're going to do now is we are going to plot each portion of the transfer function one at a time. This is the slowest approach. Once you do that several times, you will be able to use a faster approach to do the body plot for the magnitude. So let's go over the first approach, where we're going to plot each segment independently, and then we're going to add all those segments together to have the final graph. Once we do that, then I will show you the faster way or the shortcut. Anyway, so the first one will be the K, and the K here is 32 dB. So we're going to come to the 32 dB, which is somewhere around here. So this is where is the 32 dB, and we're going to have a straight line. So when we do the line, that's what we have, 32 dB. That stands for the gain of 40. That gives us 32 dB. Then I'm going to come to the 0. Now the 0 will have a corner frequency at 10, so I will start at 0 dB and I will continue at 0 dB until I hit 10. And once I hit 10, then I will read a straight line with a slope of 20 dB per decade. So it is very important that the slope of the line will be 20 dB per decade, which means that the line will break at the corner frequency at 10, but it will read 20 dB at 100, and it will read 40 dB at 1000, and so on. So now we end up taking care of the corner frequency at 10, which gives us a 0. And as you see that, you start from 0 dB until you hit a 10, and then you read 20 dB per decade as a straight line. Now we're going to come to the pole at the origin. Now the pole at the origin will pass the frequency of 1 radian per second at 0 dB, and it will have a slope of minus 20 dB per decade. So the pole at the origin will have this straight line where it will have 20 dB per decade, and it passes through the 0 dB at 1. Now when we move to the next pole will have a corner frequency at 50, so I have to come to the frequency at 50. This is 10, 20, 30, 40, 50. Here is the corner frequency at 50. It is a pole, so it's going to go with minus 20 dB per decade, therefore after. So let's do the plot for this one. So you can see that it goes straight until it hits the 50 radian per second. The frequency equals 50, right? 10, 20, 30, 40, 50, and then it goes 20 dB per decade from now on. The last corner frequency we have, it's a pole at 200. So I will locate the frequency where it will read 200. So here is the 100, that will be the 200. So this is the 200 corner frequency, and it's going to go again with as a pole, so it will be a straight line with a slope of minus 20 dB per decade. So when we do that, that's what we have. And now we end up plotting the body plot of each individual segment separately. Now when we do the magnitude and we wanted to combine all those graphs, we have to add those lines algebraically. So when we add the lines algebraically, we add the offsets and also we add the slopes, right? So that when we do the addition algebraically, I know that this is the offset where I read 32 dB, and then I have a straight line that goes with minus 20 dB per decade because of the pole at the origin. So this will continue forever. So all what I have to do is I have to offset this line, which reads minus 20 dB per decade, to 32 dB. So it will go somewhere around this area where it's going to pass the 32 dB at the frequency equals 1. And this will continue going until I hit the first corner frequency, which is 10. Once I hit the 10, then it will flatten out. So let's draw this line where I will read minus 20 dB per decade until I hit the frequency 10. So that's what I have here, is a straight line with minus 20 dB per decade until I hit 10. Now, this line has a minus 20 dB per decade continuous, but I'm going to add to it a 20 dB per decade. So minus 20 dB per decade plus 20 dB per decade, when you add the slopes, it will give me a slope of 0. So I will have a flat line until I hit the next corner frequency, which is located at 50. So now I will have a straight line until I hit 50. And then I will have, from now on, I will add the slopes. I have 0 slope. And then I'm going to subtract 20, and I will keep doing this until I hit the frequency 200. So when I do that, that's what I have is a minus 20 dB per decade until we hit the frequency 200. And now I'm going to add to this line, which has a slope of minus 20, then that will give us minus 40 dB per decade slope, and that's what we have. So this is the body plot that we have. If I delete all other segments, I will end up with the body plot that I want. This is the magnitude plot for this transfer function. Now, we can do this plot the faster way. If I practice doing body plots over and over and over again, I can do body plots straight from the transfer function without drawing all those segments and without adding them up. I can do that in my head, because the concept is very easy. You add up offsets and you add up the slopes, and you do that at the corner frequencies. So if we delete everything and we will start doing the whole graph from scratch, I know that I will start at the gain of 40, which is 32 dB. So I know that I will have 32 dB this way. But because I have a pole at the origin, then I'm going to have a straight line of minus 20 dB that will pass the 32 dB per decade at 1, right? Because I added actually the two graphs now, the 32 dB and the minus 20 dB from the pole at the origin. And I will continue doing this until I hit the first corner frequency, the first next corner frequency located at 10. So I will have a straight line that will pass through the 32 dB at 1, and it will continue going a straight line until I hit the frequency 10. So when you do that, that's what you have. See, it's very easy. You took care of the first segment this way. And now at 10, I end up having a 0, and the 0 adds 20 dB per decade. So the minus 20 dB will add plus 20 dB. That will give me 0 dB per decade. So I will end up having a straight line with 0 slope. So that will be a flat line, and that will continue until I hit the next corner frequency. So the next corner frequency is located at 50. So I will have a straight line until I hit 50, and that's what I have here. Once I hit 50, now I'm going to add a minus 20 dB per decade slope because it's a pole at 50. So I will have another straight line that will go with a minus 20 dB per decade. You add 0 to minus 20, it will be minus 20. And this will continue going until I hit the next corner frequency, which is 200. So when I do that, that's what I have is a straight line with minus 20 dB per decade until I hit the 200. Now, I have another pole, so I have to add another 20 dB per decade, so that becomes total of 40 dB per decade. So in this part of the example, what I end up showing you is I end up showing you that you can do body plots straight from the transfer function without drawing the segments of each part. Now, to come up to this level, you have to practice body plot several times. So the more you practice body plot, the easier it will be for you to do this plot very quickly. So I always tell my students that practice body plot over and over again, and then this problem becomes easy for you to do. So if you have a problem like this in the exam, you should be able to complete this problem in a very short period of time. So this is the first plot, which is the magnitude. The next plot basically going to be the phase. Now, when we do the phase, we need to see total number of zeros and the total number of poles in this transfer function. For this transfer function, we have 1, 0, and we have 3 poles. So the final angle will be the number of zeros minus the number of poles times 90 degrees. So here we have 1 minus 3, that will be minus 2 times 90 will give us minus 180 degrees. So we know that the final angle will set at minus 180 degrees. Now, if we go to the semi-log scale, that's the semi-log scale, we already took care of the frequency range from the previous plot. We said that it will start at 1 because it should be a decade before the first corner frequency. The first corner frequency is located at 10. So a decade before that will be 1, then 10, 100, and so forth. Now, when it comes to the phase, we have to be careful, right? We know that the final angle will be at minus 180 degrees. That's something we discussed. But also, because we have a pole at the origin, we are going to have an offset of minus 90 degrees. So that's where we start. This pole at the origin will start with minus 90 degrees. Then we have a 0 that will go from minus 90 degrees to a little bit up, and then it will come eventually down to minus 180 degrees. But to plot each one of those separately, I have to also include that the 0 will go from 0 to 90 degrees, and each of those poles will go from 0 to minus 90 degrees. The way we're going to do it is we want it to have 90 degrees up, but I want it to have 180 degrees down. So I will start from minus 180 degrees, and it will go up all the way until we have 90 degrees. So this is the range that I need to cover the plot of each segment for the phase of each pole and 0 in this transfer function. So I will start with the 0. The 0 basically says that we're going to go 90 degrees from a decade before the corner frequency. So the corner frequency located at 10, I'm going to go a decade earlier, will be 1. And then I will go 90 degrees in 2 decades. So the straight line will be 45 degrees per decade. So from 1 to 100, I will go 90 degrees, such that at the corner frequency, I will read 45 degrees. So let's show you how the plot will look like. If you do the plot, that's what you have. For only the 0 here, the 0 that's located at 10, you're going to have 0 degrees until you hit 1. Then you're going to have a straight line, reads 45 degrees per decade, such that it will read 45 degrees at the corner frequency. And then it will flatten out a decade later, which is at 100. So you have 90 degrees at 100. Now keep in mind that those graphs are approximates. The corner frequencies here are not exactly at 0 and 90. The one over here will be 5.7, and the one over here will be 84.3. But it will be 45 degrees at the corner frequency 10. Now we're going to come to the next pole, which is the pole at the origin. The pole at the origin will read minus 90 degrees for all frequencies. So when you plot that, that's what we have is minus 90 degrees for all frequencies. The next pole is a pole at 50. So a decade before that will be 5, and the decade after that will be 500. And it will go with a straight line of minus 45 degrees per decade from 5 to 500. So let me plot the line for you and see that when we come to the frequency of 5 around here, you will start to have minus 45 degrees per decade straight line until you hit the 500. So let's plot the line and see how it will go. So that's indeed what we have. It starts at 0 until you hit 5, then you have 45 degrees per decade, such that at 50, you're going to reach minus 45 degrees. And then it will go back to minus 90 at 500. The final pole will have a phase will start from 20 and ends at 2000, and the phase will have a straight line from 20, which is somewhere around here, with a slope of minus 45 degrees per decade, and it will last until 2000, and then it will go flat. So that's what we have if you do the plot. So it goes straight until you hit at 0 degrees until you hit 20, and then it will go minus 45 degrees per decade until it hits the minus 90. And you can see that it reads minus 45 degrees at the corner frequency 200. So the rest is easy. What we have to do is we need to add the segments of the lines. The plot of the phase usually is a little bit tricky for one simple reason, is each of those lines will have a start point a decade earlier and then an end point a decade later. So when we add the slopes, we need to know when the line starts and when the line ends, right? So let's do that and let's show you how we are going to start to add all those lines together. The first thing I want to do is I'm going to be a little bit tricky. I know that from the end of the segment over here, when we come to the end of the segment over here, I'm going to read 180 degrees. That's something I already know because I know that the final angle should be 180 degrees. So as soon as all the lines ends, I know that I should be at minus 180 degrees. And this is a reality check for us. Okay? So you know that you're going to end up with negative 180 degrees because you have 1, 0, and 3 poles. Right? So 1, 0 will be plus 90 degrees, and the 3 poles each will be minus 90 degrees. So when you add them all up, you're going to end up with minus 180 degrees. Now we're going to add all those lines here graphically. So when I add those lines here graphically, from 0 to 1, I only have the offset, which is minus 90 degrees. So when I do that, that's what I have is minus 90 degrees until I hit 1. And then from 1 to 5, I will have plus 45 degrees per decade. So I will draw a line from 1 to 5 with a straight line that will give me plus 45 degrees per decade. So that's what I have. After that, from 1 to 20, I will have plus 45 degrees and minus 45 degrees. That will give me a flat out slope. So I will have flat out until I hit 20. And now what I will have is plus 45 degrees, minus 45 degrees, minus 45 degrees. That will give me minus 45 degree slope. And it will continue until I hit until 200. And then after that, this line becomes 0 slope. And now I have 2 45 degrees per decade. So that will be minus 45 degree per decade. When I add them up, I will have minus 90 degree per decade. And that will continue until I hit the frequency 500. So I will have minus 90 degree per decade until I hit 500. And then from 500 to 2000, I will have 45 degrees per decade. And that should go back to minus 180 degrees. So that's what I have for the last segment. Now, this is the phase that you need to plot. Now, this one is a little bit tricky. You can do that from scratch, but it will be a little bit tricky. The reason is you need to know when the line starts and when the line ends, right? So you have to keep track of when the line starts and when the line ends. So let's go back and see if we can do all that from scratch without doing the other segments, right? So right away, if I have this transfer function, I know that I'm going to start with the minus 90 degrees because I have a pole at the origin. So I will start with minus 90 degrees and I will continue having the minus 90 degrees until I hit the first corner frequency, which is for 0, that will start at 1. Remember that the phase always starts a decade earlier. So I will go plus 45 degrees per decade until I hit the next corner frequency, which is at 5. So I will go plus 45 degrees until I hit 5. That's what I have. And now at 5, I have a pole which will subtract 45 degrees. So I'm going to add 45 and I'm going to subtract 45. So I will get 0 degrees per decade. So that's what I have, will be flat line like this. And that will continue until I hit the frequency 20. So once I hit the frequency 20, I stop. At frequency 20, I will have another minus 45 degree per decade. So I will have to go minus 45 degrees per decade in this direction. And that will continue until I hit the next corner frequency, which will be 100. Because at 100, the first 0 will end. So I will go minus 45 degrees until I hit the 100. Now this is gone. I took care of the whole thing of the 0, but I still have this pole and this pole. So this one will give me minus 45 degrees and this will give me minus 45 degrees. So I must go with minus 90 degrees until I hit the end of this segment, and the end of this segment will end at a decade later, which is at 500. So this will go minus 90 degrees per decade until I hit the 500, and then I will have 45 degrees, minus 45 degrees per decade for this pole until I hit the frequency 2000, and then I took care of all of the zeros and the poles in the transfer function. I flatten it out at 100 and at minus 180 degrees. That is basically body plot for the phase body plot of this transfer function. So practice those transfer functions, and the more you do those kind of problems, the easier it becomes for you. And body plot is a very important tool engineers use. The most important reason is most of the data sheets of the components that we use will show you the performance based on body plot. So body plot is a very important tool for us to use and understand, because most of the data sheets use body plot to describe the behavior of their components. I hope you enjoyed this example, and good luck to you.
Please take note that the example gives you a body plot that is plotted out with, started with asymptote and then the summation. I would prefer you in any of the tests and exam not to delete away the asymptote, because each of the asymptote will give you marks. Therefore, please keep the asymptote there while you sum up. Now, of course, people might argue that I can use the other method whereby I just arbitrarily looking at the transfer function and draw out. I don't advocate that, because you will make a lot of mistakes if you are not careful. So basically, draw out the asymptote and then sum them up. That's the best way. Okay. Now, next video we'll talk about. Next, we will proceed on to see the uses of this magnitude and phase plot.
Once the final plot for the magnitude and the phase are on the same semi-log paper and they are sharing the same frequency scale, we can now proceed to read the phase margin and gain margin. For reading on phase margin, we first identify the frequency, omega GC, at which the magnitude plot cross 0 dB. Project omega GC downward until it cut the phase plot. The distance of the value where it cut the phase plots to minus 180 degree will be the phase margin. PM. For reading on gain margin, we first identify the frequency, omega PC, at which the phase plot cross minus 180 degree. Project omega PC upward until it cut the magnitude plot. The distance of the value where it cut the magnitude plot to 0 dB will be the gain margin. GM. Note that as long as the gain margin and phase margin falls within shaded yellow area, the region bounded by 0 dB and minus 180 degree, the phase margin and gain margin are positive. If the phase margin or gain margin are outside the shaded region, they are negative. With that understanding, we can use the table on the top right-hand corner to determine the stability of the system.
Now, this is the slides that explain what we use or how we use the gain plot, the magnitude plot, which is on top, and the phase plot that is at the bottom, to determine the stability. Now, basically, that's the reason why you need to put your magnitude plot on the top half of the graph paper and the phase plot on the bottom half of the paper, and their frequency should align, right? The frequency should align. So by doing so, you are able, once they align, you are able to check the crossover and then find out what's the phase margin and gain margin. Now, if they are not aligned, then you will read all the wrong values. So the alignment of the vertical alignment of the frequency of the gain plot and phase plot is very important in determining the phase margin and gain margin. If you determine the wrong phase margin and gain margin, then your analysis of whether the system is stable or not will be out. So therefore, that is very important, the alignment. Now, once you have the plot put onto the together, aligned, and then basically you are ready to decide what is your phase margin and what is your gain margin, and finally deciding whether this is stable or not stable. Now, let's first start looking at, there's two reference point I want to take caution you. For the gain plot, the reference point is 0 dB, right? 0 dB is your gain plot reference point. And the phase plot, the reference degree is actually minus 180 degrees. So basically, these two lines are the reference respectively for gain and for phase. So now, for the phase margin, we will look at when the gain plot cross the reference. So when the gain plot cross 0 dB, which is reference, I check this frequency, we call it omega gain crossover, omega GC, and we project this thing down. We look at the phase where it crossed this line, omega GC, and we check the point till it reach minus 180 degrees. The angle between this and that will be your phase margin. Right? Will be your phase margin. Now, likewise, for the gain margin, we will check the phase plot when it cuts its reference, which is minus 180 degrees. And when it cuts the reference, this frequency will be omega PC, which is omega phase crossover. Now, when you project this omega PC up to the point where it cuts the gain plot, this very gain to the point where it's 0 dB, this will be your gain margin, right? This will be your gain margin. So basically, that's how you read your gain margin and phase margin. Now, of course, there are situations. Okay, then the next thing is, how do we check whether it's stable, even though we got the gain margin and phase margin? Now, remember, there is this shaded region. If you look at the picture itself, I deliberately draw out the shaded region, which is in beige in color. And this shaded region is bounded by your two reference. One of the reference is the 0 dB, the gain reference, and the other reference is the minus 180 degrees, which is your phase reference. Now, bounded by these two reference is the shaded region. Now, the moment you do and you're cutting your measurement, your result come out, your phase margin and gain margin is within this shaded region. They are known as a positive and positive gain margin and phase margin. So the moment both of them are positive, then we say that the system is stable, right? Now, of course, there is situation whereby if your gain plot goes to cut exactly at 0, so there is no gain phase margin at all, then you have a 0 phase margin. And when you have that, it is called a marginally stable. Now, of course, there is situation whereby both of them are also negative. Now, the moment when the phase plot goes below, and then your phase margin will be what? Will be outside, right? Because it will be outside from your cutting to your minus 180 degrees. It will be outside of the shaded region, and therefore the phase margin will be negative. Likewise, if the gain suddenly move upward, so your cutting, the point where you cut will be on top here, and to the 0 dB, it will be outside the shaded region. And because of that, your gain margin will be negative. So if it is both negative, of course, it's unstable. So using this rule of thumb, we are able to say that whether the system is stable or not stable. Okay?
Please watch the Bode stability analysis example to have an animated idea how to check phase margin and gain margin and determine stability.
You can perform stability analysis on a Bode plot under these conditions. First, you assume that you have the Bode plot of the open loop system, so just of G of S. Then you assume that the system will be in unity feedback, the negative, and you assume that G of S is stable. So you assume no poles or zeros in the right half plane. There are two stability criteria, gain margin and phase margin. In order for a system to be stable, the gain margin must be greater than 0. The gain margin is the gain of the system at 180 degrees of phase. We'll do some examples to show that. And the phase margin must be greater than 0. And the phase margin must be greater than 0, where the phase margin is 180 degrees plus the current phase at 0 dB. Essentially, that's the amount of phase that you have less than minus 180 degrees. Here's a little bit of insight into that. If you think about the gain, we have a system that goes like this. So we're putting something in and something comes out and we're feeding it back through. If everything that goes in comes out smaller, then the system has no way of growing because whatever you put in keeps coming out smaller. That's called the small gain theorem, and it's related to the gain margin. The other thing you have here is something going in and coming out, and then you're subtracting it. As long as when you subtract it, you're subtracting it so it becomes less. The problem is that when this phase shift changes more than 180 degrees, 180 degrees phase shift is like a change in sign. So if you put in a positive number here, it comes out negative, then you change the sign again to subtract it becomes positive, you add it back in, you can see it keeps growing and growing, and that's related to the phase shift. Here's an example. I've taken the transfer function 50 over the quantity s plus 1, s plus 11, gone into MATLAB, and got the Bode plot for this. And I want to know what is the gain and phase margin for the system. So for the phase margin, you look for where the system crosses 0 dB. It's right there. Then you come down and you look for the distance right there. That's the phase margin. That's the amount of phase that you have before the system has 180 degrees of phase. Because once it has 180 degrees of phase, then remember the feedback changes sign and you're essentially adding something back in. So in this case, it looks like we have a phase margin of about 90 degrees. The next thing you should look for is the gain margin. The gain margin is the amount of gain that you have when the phase crosses minus 180 degrees. Let's see. So the phase goes, well, the phase never crosses minus 180 degrees. That means that the gain margin way out here is infinite. The gain margin is infinite because the phase never crosses 180 degrees. This should make sense if we look at the root locus for this system. We have the plant and we're doing it in unity feedback with a gain of k. So the root locus, the two poles, one at minus 1, minus 11, come together in the middle, break apart, and go like that. That means that no matter how much we increase the gain, the system never goes unstable. Let's look at this. Increasing the gain is the same as moving this up. That corresponds to increasing gain. And if you go back to the rules for generating Bode plots by hand, you realize that that's the case. If we increase the DC gain, we essentially just raise the position of the gain curve. Well, the phase never goes to 180 degrees. So no matter how far up we raise this, we're always going to have a gain margin that's infinite. We're also going to have a phase margin because you see as I raise this up a little bit further, I'm going to draw what it would look like. Well, then I come down here and I look at the new phase margin and it's going to be, it's going to be less, but it's still going to be greater than 0. And because it never crosses 180 degrees, no matter how far up I raise this curve, I will always have some infinitesimally small phase margin. So the system will always be stable no matter what the gain is. And I can see that right from the Bode plot. That corresponds to what I know from the root locus. One last example. The transfer function for the system is given here. You can see it has a pole on the real axis and then a complex poles with a damping ratio of 0.1 and a natural frequency of 10. The corresponding Bode plot is shown here. Let's look for the gain and the phase margin. First look at the phase margin. We look for where the system crosses 0 dB. It looks like it crosses 0 dB right about there. So come down and there's 180 degrees. So we have quite a bit of phase margin here. So in terms of phase margin, the system has good stability. Now let's look for the gain margin. The gain margin, you look to see where it crosses 180 degrees right here, and then you go up to see what the corresponding gain is. And there's the gain. So looks like we have a gain margin maybe of 10 dB and a phase margin of, I'd say, 160 degrees. This plot also tells us what happens if we increase the gain. Remember, increasing the gain is the same as moving the gain curve up. As I move the gain curve up, the crossover point for 0 dB moves along this line. It moves out. And as it moves out, you can see that the phase margin becomes less and less. Eventually, we get down here and we can get a gain that's large enough. If we push the whole curve up so it looks something like this, we now have a negative phase margin, so the system becomes unstable. The same thing happens for the gain margin. As we increase the gain at 180-degree phase, at some point, the gain is greater than zero. That will result in instability. So we can see that by increasing the gain, in this case, the system can go unstable. In its current state, with a gain of 1, the system will be stable. But if we increase the gain, it could go unstable, and we can verify that again with the root locus. Our system has a real pole at minus 0.5 and then complex poles at -1 plus or minus just about 10. The root locus for this, let's see, we have 3 poles, so we need 3 zeros. We don't have any real zeros. They all must be at infinity, so we've got a infinity 0 out here, and then 3, we've got them here. So the root locus probably does something like this. Well, you can see what happens here is that as we continue to increase the gain, eventually the poles cross the imaginary axis and go into the right half plane and the system becomes unstable. Now, the root locus tells you that that happens, but what it doesn't tell you is what value of gain would be required to make that happen. If you go up to the Bode plot, you can actually calculate the gain required to make the system go unstable. And in this case, if we look at 180 degrees of phase right here, and we go up, we see this gain right here. If we increase the gain by that amount, then we'll have a negative gain margin, and the system will go unstable. So it looks like if K is somewhere around 15 dB, the system would be unstable. I'm going to go through and just verify that. I can calculate how much gain will be needed to raise the gain curve up so that it now has a positive value of gain when there is a 180 degrees phase shift. I calculated the gain of about 15 dB. I'm just eyeballing it from the graph, so I'm not going to be that close. That corresponds to a gain of 5.6, or K of 5.6. I do the closed loop characteristic equation for that with a K. Put K is equal to 5.6. Solve for the roots of the equation, and I get S is equal to 0.34 plus or minus 10i and minus 3.2, which indeed the system is unstable. And you could fool around and do a little bit more careful measurements. You'd find that the actual gain is somewhere like 4.9. So you can see the Bode plot and the root locus relate. And from the Bode plot, you can actually get the gain that's required on the root locus to cause the system to go unstable.
Now, for this particular video, of course, it's very good and clear in terms of explaining how you find the phase margin and if you shift the gain, how you eventually may get a negative phase margin or negative phase gain margin. But please ignore the root locus part because that is out of our syllabus. But if you are interested, you can come and look for me. I will explain to you. That is maybe the university level. So please don't worry about the root locus portion. Okay.
Please watch e-tutorial 14.
Okay, so because this week the lecture is quite a lengthy one, so our tutorial we are only going to focus on the book plot, stability book plot for question number 7. So let me fetch the question. Let me stop sharing first and let me go and fetch the question. Question 7, right? Okay, if I were to share with you the question, so basically the question is the question 7 is 40. You have a transfer function of 40 times by 0.25 s plus 1 divided by s plus 2, 0.5 s plus 1. So basically, you have so many 1, 0, 3 poles, and you have a k that is not really 40 because it's not normalized yet. So if you normalize and bring everything out, then that will be the actual k. So they ask you to draw on a semi-log paper the asymptotes of the book plot and the phase plot of the system. So basically, draw your book plot, and then determine the phase margin and gain margin, comment whether the stability. This is a very standard book plot question, asking you to do the block plot, and then after you put a book plot, determine the phase margin and gain margin, and ask you whether is the system stable. So if you are very confident in plotting that you will not get error, then basically this is 100% you can score, right, for the book plot. So some people would just like to be certain. They don't want to try other luck. So they just say, this one is difficult to do, but as long as I practice long enough, I'm good at it. So I will definitely score for this one. So basically, they just do both. They try to memorize the step. In fact, it's not memorizing. It's be consistent, keep practicing, then you'll know how to draw. So basically, I'm going to directly share with you the solution for question 7, because in view of the time, give me a while. Let me find the solution. Okay, maybe I'll share in a while time. So for the next tutorial, we will discuss more questions. But as for now, we will just do question number 7, right? Okay, it looks a little bit complicated here. It looks a little bit complicated here because if I show you everything at one go, then it looks rather complicated. Why not this way? I just do it in the whiteboard and basically by basically sketching, and then later we will look at the actual one, so that basically you all will roughly get an idea. So basically for the transfer function, it is 40, right? 40 is the gain, and then of course you have times by 0.25, 0.25 s plus 1, right, over s plus 2 and 0.05 s plus 1. Now, so you have 1 0, 1 0, 3 poles, right? Simple as that, right? So what is this roots for this one? So you equate this 0.25 to 0, 0.25 s plus 1 equals to 0. So s is equals to minus 4. So your roots is at 4, right? So the first one, the roots is at 4. This one, the roots is at 2, right? S plus 2 equals to 0. Your s is equals to minus 2. This is at roots at 4. This is at roots at 2. And then this one is 0.05 s plus 1 equals to 0. That means s must be equals to minus 20, right? 1 divided by 0.05 is 20, right? 1 divided by 0.05. So it's 20. So basically, you got basically all your poles down here, right? So of course, if you want to normalize it, you want to normalize your G, your open loop gain, and this is your GH. If you want to normalize everything, you may do so first. So basically, if I want to normalize, this is already normalized, that's good. Then this one you want to normalize, you bring out a 2, so you have 40 divided by 2, right? So this one is 0.25 s plus 1 is the same, no change. So then your s no change. Of course, this one you divided by 2 will be 0.5 s plus 1, right? Because you divide this by 2, divide this by 2. So the other one is already in your 0.05 s plus 1. So these are all normalized, right? So now your gain is essentially 40 divided 2 is actually 20. So your gain is actually 20. So we can We draw this as 20, right? 20. So for your first plot, of course, we got to determine. Let's say this is your, let's say this is your x-axis, right? This is your frequency, right? Of course, this is your frequency, and then of course, first of all, you got one frequency of 1, which you are interested because there is a roots at origin, so you have 1. Of course, you also have 2, right? 2 maybe here. And of course, 3 get closer, then 4 get even closer. 4 maybe here. You get 4, right? And then of course you get another one, 5, 6, 7, 8, 9, 10, probably 10 here. Like 1 to 10, 1 to 10 is here. Then 1 to 10, then 10, 20. The next one is 20, right? So it's about here. So I'm trying to estimate what is the log scale, right? What's the log scale? Now, with that, then we start to plot the asymptote, right? So the first asymptote is at 4, right? The first asymptote is at 4. Let me use a blue color, right? For this case, it's at 4. So basically, you start with 0 dB, go all the way down here. Then at 4, you move up by plus 20 dB per decade. 20 dB per decade, you must say 4 to 40, right? Let's say 4 to 40. 40 point, then you check, is it at 20 dB? Oh, so that's how you check, 4 to 40, 20 dB here. So it's a 20 dB per decade. So that's your first 0 asymptote, right? Right. Then for the next one, it is a pole that cuts the x-axis at 1. And that one, let me represent by this, also at minus 20 dB per decade, but it is a pole, right? So it's like that. So this is your, of course, just now I should label it. So this is your 1 over S. Just now that one is basically your, just now that one is basically your 0.25 S plus 1, right? So this is the 2 line. Now, how about S plus 2? S plus 2 will have a pole at 2, right? Pole at 2, let me use green. So basically a pole at 2 will be something like that. It will turn out at 2. And this is your 1 over S plus 2, right? Or 0.5 S plus 1. Any way you want to indicate it. So this is your, the other one. Of course, all these are to infinity and to infinity. Then of course, the last one is at 20, right? So at 20, let's use another color, maybe orange. And with orange, you will have all the way up to 20. And you got the next pole coming down, and again, all the way to infinity. So you get all your poles set up. And then of course, this is 20 log 20. So what is 20 log 20? 20 log 20, you get about 26, right? So the other one, this K will be 26. So let's use a purple. Then you get 26 dB here. 26 dB. This is your K. And this is your 20 log 20. Okay, 20 log 20. So basically, that's your gain plot for all the asymptote. Then the final gain you need to put in is how to sum all these things up. Now, of course, the way I do it is I don't like to sum the shift together. So let me do. So your original must be following this line, right? Because everything is all 0 except this line. So your original must be following first this line, right? First this line. Then when it comes to here, what happened? It continued this line, right? It continued this line at minus 20 dB per decade, right? Now as it come to here, it become 2 line. Minus 20 dB, it become minus 40 dB per decade. Right? From minus 20 dB per decade, it jumped into minus 40 dB per decade. Because it from 1 line become 2 line, right? So you go all the way up here, it goes back to minus 20 dB per decade because this guy is 1 minus 1 plus 1 minus 1 become left with 1. So it's become minus 20 dB. So you see here is minus 20 dB per decade. Here at this point of time, here is minus 40. And here it go back to minus 20. Right? So go back to minus 20. And when it hit here, 3 of them is minus 20, right? And all the way up to here, it go back to minus 40 at this point. Because now I have 3 versus 2, right? So it will be 2 down. So it become minus 40. Oh, so about minus 40. Also, your net curve is something like that for your game plot. So let's do a check with the actual one that I showed you just now. So you can see for this final game plot is slope down, down from minus 20 to minus 40, back to minus 20 and back to minus 40 again. Of course, this is a shifted. We have not, for just now that plot, we have not shifted. We have not shifted. So basically, if you want to shift this, basically, let's say if I represent by another color, like green, this guy, the best point to choose to shift will be this point, right? Because this point is 0, you add with 26, it will be 26 exactly at this point. So from this point, you basically follow the line, right? How it slope, at this point it slope, then it slope down, slope up, or something like that. So you basically shift up entirely from this point. Making sure that the line is in parallel. The rest of the line is in parallel, but it must cross this point. Okay, so that's how you shift your. That's how you shift your this line up. So of course, the final one will be the shifted up curve. Now, let's also talk about the phase. Phase, how you plot it. Maybe I should clear the gain, because the gain, if I put here, maybe later you all cannot see what I mean. So I just clear the gain first. Right? Then I will go through the phase with you. Okay. So same thing. Of course, now we know that this guy here, will introduce 0 phase, so nothing to worry. This guy here will introduce a minus 90 degrees phase, right? So then that is left with this 3, right? So if I start my, of course, that's the thing that I need to take care is basically this 3, right? So let's start with 2 first. So with 2, you got to look at 20, and you got to look at 0.2, right? And this 2 is at a denominator, so it must be sloping down to this is minus 90 degrees line, right? So let's say this guy is red color, so it must be flat originally, right? And then it must go down to minus 90 at 20 radian per second. So that's how it should look like, and it will slope down. So that is your phase for 1 over s plus 2. Okay. Now what about the 20? 20 will be 2 and 200, right? So it will be 2 and 200. Be 200 here. Let's say 200 here. Then you have the line. And let's say if I use green color right now, so it'll be 2 and 200, right? So at 200, it should hit here. So 2 and 200. Of course, this is another line that overlap here. Another, it should go from here to there. Okay, it should go from here to there. Okay, so this will be your, so to say, 1 over 0.05 s plus 1. This will be this guy here, right? Now, what about the other one on top? That is 4, right? So basically, for 4, I got to redraw the thing. Let's say this is 4. Then this would be 0.4, right? And this would be 40. Okay? So of course I have to take care now because it is because right now is on top, right? Because it's a 0, so it must go. How come I keep drawing the crooked line? Okay, so let me be more careful when I draw. So let's say this is your positive 90 degrees line. So right now for 4, let's say, let me use a blue instead. Right, let me use a blue. So basically it's 4 to 40. So at 40, you should hit there. So basically your line should goes up this way. Right? And then of course it goes straight all the way. Right? So it's here to there, and then this guideline here, it will be 0.25 s plus 1. So you have your 4 asymptotes all drawn out. So then basically what you need to do is sum them up. So basically if I use back the same, so you started off at 90, right? Because you have a 90 degrees. The 0, I don't care. Right? So I started off at 90 because everything summed with 90 will be here. This point here, right? Then at this point, it will tilt down a bit, right? Because it occur at 0.2 first, tilt down a little bit. Until it hit 0.4, it becomes flattened, right? Become flattened. Flattened for both cases until it hit 2. Right? Until it hit 2, it's flattened. Right? Now when you hit 2, you have this guy, this guy, this guy. So 3, 2 down, 1 up. So it's 1 down. So 1 down for until 20. So it's 1 down. So 1 down for up to 20, this guy stop. So there is only, and this guy stop first, right? So basically, if this guy stop, then this and this will match, right? So there's flattening. Flattening all the way up to 40, right? Because at 40, the other guy also stop. Oh, this guy also stop. So it's flattened at 40. Then, of course, after it flatten, this guy also stop at 40, then you will follow this guy. Follow this guy at minus 20 dB per decade, and you will, when you hit 200, you will flatten. 200, you will flatten. So what is the net result? So you got this guy at plus 90, and this 3 is minus, minus, minus. So it's plus and minus cancel. So it's actually, the end result should be minus 180 degree. Oh, so that's how the phase would look like. Now, if we take a check at the actual plot, we check at the actual plot. Let's see. Yeah, you can see that it come down, go down, come down, go down, and hit minus 180 degrees. So that is your net result. Okay. So that is how you plot your phase and gain and sum up all of them together. Then, okay, now the question is to determine the stability. Now the first is look at the gain crossover point. That means the net gain crosses the 0 dB. You look down and you look at the phase and you check the phase between here and minus 180 degrees point. It reads about 54. So your phase margin is positive 54 because remember your shaded region is bounded by 0 and 180. So it's still above inside the shaded region. So it's 54 degree. Now for the phase, if you touch 90 degrees, 180 degrees, that's the point where it cross. Then you look up, right? You look up on top here and you see that, hey, it crossed here. And basically from here to 0 dB is about 50. So your gain margin is 50. So since your gain margin is 50, which is positive 50, phase margin is positive 54. So both of them has positive phase margin. So what does it mean? It means that the system is stable. Okay, so that's what the question 1, right? Question asks. Okay, so we have drawn the things. We have determined the phase margin and gain margin. Comment on the stability. So the stability is if you have a positive phase margin and a positive gain margin, the system must be stable. Okay, so with that, we finish question 7 of tutorial 4, and then we finish the discussion on phase and gain margin and all the asymptotes plotting. I think it's quite heavy. So with that, I will end the session here. Thank you for the attention, and Have a nice day ahead.